Hi, I'm Michelle Minitti, a Flinn Scholar from the class of 1991. I went to McClintock High School in Tempe, and I went to the University of Arizona. I'm going to tell you a little bit today about my journey from the Flinn Scholarship to one of the jobs I have today, which is a science team member on the Mars Science Laboratory mission. My journey really starts when I was in the third grade, and I did an independent study project on black holes. And from that moment on, I was hooked on space. I wanted nothing more than to be an astronaut. And my desire to be an astronaut came up in my Flinn interview. I got into a bit of an argument with one of the interview committee members over robotic versus human exploration. We went back and forth a few times, and my final exasperated reply was that we needed human exploration because otherwise I would be jealous of all the robots. And that elicited a laugh from the interview committee. And I thought I had doomed myself by getting into an argument with one of the interview committee members, but it ended up working out okay. I went to the University of Arizona where I studied material science and engineering. The Flinn first travel experience for me was going to Europe with Dr. Ray White and Dr. Donna Swaim on their legendary ancient art and archaeoastronomy trip. It was quite a combo, both the professors and the topics. The financial freedom of the Flinn gave me the chance to get my pilot's license one summer, a key skill for a wannabe astronaut. My faculty mentors encouraged me to apply for a space grant fellowship, and that was my first introduction to research and all the highs and lows and struggles and successes that go with that endeavor. And Space Grant in turn led to a NASA internship, the benefits of which I still am reaping today. I had a little bit of free time in my schedule, my junior year in engineering, and so I ended up taking an elective in planetary science. I wanted to get a little bit of space into my education. And it was there that I discovered that I could do material science on planets. I had a class in material science in ceramics, not pottery making, but high temperature oxide materials that are made up of silicon dioxide, magnesium oxide, aluminum oxide, oxides like that. And these ceramic compounds had the most interesting names. I found them to be almost lyrical, like forsterite and cristobalite and phaolite. And it turns out these ceramic compounds were minerals that make up planets. So when I discovered that I could link material science and space, I started to look into geology for graduate school. My faculty mentors were a little puzzled, but nonetheless, they were very helpful and supportive. They put me in contact with some of their colleagues that were in geology. I managed to find geology graduate schools that would take someone with my non-traditional background. And I ended up going to Brown University in Rhode Island. But before I headed off to grad school, I used my final Flinn travel opportunity to go to geology field camp. My senior year at U of A, I took a few geology classes, so I had kind of basic terminology, basic processes, basic concepts under my belt. But geology field camp is really the capstone experience for a geology major. It's where they put all of their classwork together into going out into the field and mapping structures they've never seen before. So me going to field camp was a little bit like knowing basic arithmetic and then going into a calculus class. It was a struggle for sure, but it was very much a jump in the deep end to learn to swim, learn by doing experience, that I still again benefit from to this day. Geology graduate school wasn't quite so much of a struggle, but the biggest struggle ended up being when I learned early on in grad school that the astronaut corps was closed to me. This was the early days of the internet message boards, and there was a message board for people interested in becoming astronauts. So people like me, people who had been through the very arduous, intense interview process, and people who actually had made it through the process, newly minted astronauts, met together on this message board and shared tips and tricks, lessons learned, hints about the interview process. And one person in particular talked about how they overcame a report of early childhood asthma. They went to a pulmonologist, they took this particular test. When you pass it, then the flight surgeon at NASA gives you the check mark that you're okay. So I thought, well, I have asthma. It's not bad. I take a couple puffs on my inhaler before I go out for a run, nothing life-threatening, but I better go check this out. So I found myself a pulmonologist, took the test, and failed it immediately. It wasn't even close. So there I was in grad school, and the whole point of going to grad school was gone. So I thought, well, what do I want to do? Do I want to keep going? Do I want to switch careers? I ended up calling my faculty mentors back at U of A to talk to them about ideas. One of them had gone on to a career in consulting, so I talked to him about that life. But fortuitously, it was about July 1997, NASA landed the Mars Pathfinder mission on Mars. It was the first time NASA had landed on Mars in 20 years. And that little rover immediately started making discoveries that I was poised to look into with the kind of training I had thus far in grad school. I would learned how to do high temperature, high pressure experiments on rock compositions. And by changing the conditions of those experiments, try to recreate the conditions by which a planet would make a rock. So I was able to take those results from Mars Pathfinder, take them to the lab, and recreate the compositions that the rover was measuring. It ended up being my first paper. And that also was the beginning of NASA's Mars exploration program. NASA sent missions to Mars every 2 years, some of them successful, some of them not so much. But what it meant was that there was a steady stream of results coming back from Mars, new discoveries, new insights into Mars and its processes. And I could go to the lab and design experiments and design research to try to address these new findings. And I found that really fun and really fulfilling. And it was definitely enough to keep me in grad school, definitely enough for me to want to pursue a career in it. It was a way I could participate in space exploration without actually being able to go myself. Research took me to a postdoc back in Arizona, this time at Arizona State. I ended up working at the Center for Meteorite Studies. And about that time, one of my friends from grad school reached out to ask me if I was interested in joining a team that was writing a proposal for a camera to go on the next Mars rover. This was the Mars Science Laboratory. At this point, the Mars exploration rovers, Spirit and Opportunity, were just at the beginning of their very long, successful lives on Mars, and NASA was already planning to send the next rover to Mars. So our proposal would be for a camera to go out on the end of the arm of the rover, and it would get up very close to rocks and look at them in very high resolution. High enough resolution that they would be able to resolve grains of sand inside targets. And that would tell you if that rock was born in a Martian sand dune or a Martian river or a Martian sea. And by looking at rocks in that high resolution, you're able to discern the processes and their origin, where those rocks came from. So the camera was called the Mars Hand Lens Imager, MAHLI, M-A-H-L-I. Everything in NASA is an acronym. So I was really excited but hesitant. I didn't know anything about cameras. I didn't know anything about missions. I didn't know anything about mission proposals or instrument proposals. So I worried about being able to contribute. But the appeal of being able to participate in that kind of experience was too much to pass up. So I said, yes, I was on board, all in. And if all I could do as I was learning the ropes was get them coffee, then that is what I would do. So I helped write text for the proposal. I helped make figures for the proposal. And in December of 2004, we found out we were selected for flight. We were not due to launch until about 5 years later. It takes a long time to build a rover and its instruments and the subsystems when the rover is the size of a car, 2,000 pounds. And it ended up being technically challenging enough that the launch had to be postponed by 2 years to give us more time to build everything. And that 2-year delay is because Mars and Earth are only aligned every 2 years or so to minimize the amount of time it takes to travel from Mars to Earth, and minimize means 6 to 9 months. We ended up launching in around Thanksgiving of 2011, and we were due to land in August of 2012 in Gale Crater. Gale crater is a very large crater on Mars, and we hypothesized that it was the home of an ancient lake, which is why we wanted to send the Mars Science Laboratory there. At this point, the Mars Science Laboratory rover had been nicknamed Curiosity. So the landing process, or entry, descent, and landing, EDL, is a very complicated process. It's also affectionately known as the 7 minutes of terror. And that's because in 7 minutes, you go from a speed that you're traveling from Earth to Mars, about 13,000 miles an hour, down to 0 miles an hour on the surface of Mars. And you slow yourself down in a number of steps. First, you use a heat shield, and the friction of the atmosphere against the heat shield slows you down. Once you've slowed down enough, then you kick out a parachute, and you slow yourself down using that parachute as you slowly get closer to the surface. And once you're close enough, you use rockets to take you the rest of the way down. But instead of the rover having rockets, the engineers designed basically a jetpack for the rover, and the jetpack was called the Sky Crane. So our rover would ride down to the surface on this jetpack, and as it got really close to the surface, the Sky Crane would lower the rover down to the surface on tethers. And when the rover was gently touching the ground, the jetpack would cut itself off and fly safely away. We were the first mission that was going to use this landing technique on Mars. And every step of that process is monitored by the engineers back on Earth. There's nothing they can do about it. Everything is automated. You can't joystick it from that far away. So you had to wait to hear what was happening. But the kicker is that it takes time for signals to go from Mars to Earth. And at the time that we landed, the amount of time it took a signal to go from Mars to Earth was about 14 minutes. So even though we would get the signal that we had just entered the Martian atmosphere, the rover was already on the ground in one piece or multiple pieces, and we were just waiting to find out. So it was a very out-of-body experience, knowing that the universe knows the answer. The answer exists in the solar system, and you're just waiting to hear what it is. But we waited, we got all those signals back, and when we found out that we had successfully landed, the group of scientists, the rooms of scientists that I was in, just burst into cheers, tears, screaming. Everybody was so thrilled that we had safely made it to the surface. And I can go back and watch the YouTube video of that process, of the mission control engineers reading us off every step of that landing process. And while I watch that, my heart races the whole time. And when we land, get that successful signal, I burst into tears. And even though it's 8 years later and I know the answer, the emotion of that moment just never goes away. And of course, the excitement for the scientists really had just started. We successfully were on Mars. We got to operate the rover now. And to make the most of our time on Mars, while the rover slept on Mars, we worked. We built a plan. We figured out what the rover would do the next day. We would send that plan. The rover would wake up and execute that plan. And we were sleeping while that was happening. The rover would send us the data at the end of her day. We'd wake up and the process would start again. But to do that, there's a catch. You have to do something called living on Mars time. It's because the Mars day is 24 hours and 39 minutes long. And so let's say it's 8 a.m. in California, 8 a.m. Pacific time, and it's 8 a.m. local time for your rover in Gale Crater. Well, you go through a day, a Mars day, and it's 8 a.m. again for your rover in Gale, but it's 8:39 a.m. for you in California. So if you want to stay in sync with the rover, you have to move your day forward 39 minutes every day. So after about 2 weeks of this, it's 8 a.m. for the rover, but it's 8 p.m. for you. So there were days that we would go into work at JPL and we would it would be 3 in the morning and we'd be showing up for work. And there were other days that it was 3 in the morning and we would go home to have dinner. You can imagine Mars time is really not sustainable for very long. We did that for about 3 months. And after that, we all went back to our home institutions. At that time, we were all co-located in California together. And we still plan that way to this day. We're clever enough and we've gotten good enough at planning that we can keep the rover busy every day on Mars, even though we only plan a few times a week. But we use tools. We use the phone. We use video conferencing tools. We use chat tools to communicate with one another. We have common databases and common planning tools that we use together so that we're all on the same page and we can build a plan for that rover every day. And it's exciting and it's a privilege to get to do that every day. And every day is exciting because every day is a new puzzle. The rover has constraints on what it can do every day. You only have so much power. There are only so many communication windows you have. Sometimes instruments can't operate at the same time as one another. Yeah, sometimes it's too cold for the rover to operate. So you have these constraints, but the scientists are still trying to get every bit of science out of that rover every day possible. So we are always working to solve that puzzle. It's very much like you trying to pack the back of your moving van for a cross-country move, and you are cramming everything to every nook and cranny, shifting things around to get everything to fit. And that's very much what we're doing with our science every day with the rover. Once that plan gets sent up to the rover, then you can monitor what time it is on Mars to keep track of what the rover is doing. Anybody can do this. You can go to JPL's Curiosity website and see what time it is in Gale Crater. And I will do this sometimes, and I will know that sitting in my office looking at that time, I know that the rover is taking a picture that I asked it to at that very moment through hundreds of millions of miles of space. And that is a very unique and special feeling, to feel that connection with something through the solar system while you're sitting in your own house. The next excitement is waiting for the data to come back. There are only so many communication windows that the rover has. The rover sends data to orbiters around Mars, then those orbiters talk back to Earth, and you end up with just discrete windows during the day in which you can communicate. So you know your image has been acquired, but then you have to wait for it to come back. And that wait is very much like a child waiting for birthday presents or holiday presents. There's an almost greedy anticipation waiting for the new data to come back. And when those new data come back, it's always a thrill. You get to be one of the first people in the world to see this new place on Mars. What does this new target look like? What does this new vista look like? What does our new selfie look like, as our rover likes to take? It's always a thrill, and it's always wonderful. And the fact that we're doing this 7.5 years after landing is of course a testament to the engineers that built Curiosity, but it's also the result of scientists and engineers and their dedication to the mission. Curiosity is a robotic mission, not a human exploration mission, but every act she takes on Mars is the result of people showing up day after day to find something new and to push exploration forward. And our team is connected by that dedication to the rover and to the mission, but also to one another. And that's something we can feel, even though we are spread across the globe, we can still feel that through our planning process every day. And that connection is something I could not have anticipated when I argued so strongly for human exploration back in my Flinn interview. And I couldn't have even envisioned that this job existed back in those days. But in many ways, it really feels like the job that I was meant to have. So when I was a kid, I had a poster on my wall, had an astronaut, of course, and it said, "Shoot for the moon. Even if you miss, you'll land among the stars." Well, in my case, I landed on Mars. So thank you for listening, and thanks to the Flinn for helping make it possible.